Welcome to Euler's method and error. So note, Euler's method is used for numerical approximation. It does not give exact values. So, Euler's method is used for numerical approximation. And it does not give exact values. So there are a couple pieces that contribute to the error. First up, when we use the tangent line approximation, that itself is an approximation for our solution, right? So whenever we use the tangent line approximation, we are approximating the solution. And then also each time we set our new initial condition, that new initial condition is already off due to the tangent line approximation. So each time we set our new initial condition, the y value itself is already off. From the previous tangent line approximation. So essentially, we kind of expect the error to snowball. Because not only do we use our tangent line approximation, which will give us a wrong value, but now the next tangent line approximation we use is not even starting off from the actual solution. It's starting off from our approximation. So we're going to look at the example we were working with previously and see exactly how much error we could use. So let's take the y prime plus 2y equals 3x squared e to the negative 2x with y of 0 equals 2. This is a non-homogeneous linear first order differential equation. So this is a linear first order differential equation. And we learned how to solve this in we learned how to solve this in section 2.1, right? So we learned to solve this in section 2.1. And the actual solution is y of x is equal to x cubed e to the negative 2x plus 2e to the negative 2x. So I went ahead and copied the values from our previous problem, or the calculating by hand. Xi, Yi are what your book uses for each new set of initial conditions, essentially. So on the left here, this is from the previous video. So this is from the previous video. And then on the right, we have the y values from the actual solution. So this is the y values from the actual solution. So as you can see, the error starts off being pretty minimal, but for each step we take, the error seems to get larger and larger and larger. The actual value of y of 5 is 0.7817. We had found it with Euler's method to be 0.6951. So we only did 5 steps, and there's a pretty significant error already. Right? So note, after just 5 steps, of step size 0.1, the error is already 0.6951 minus 0.7817. And so this is already approximately 0.09. Right? So we're close to a 0.1 difference already. Negative 0.09. So Euler's method is underestimating the actual value by around negative 0.09. Right? So if we went more steps, the error would likely get even larger. So in the next video, we will see how to do this in Excel, and that will save us quite a bit of time and work.